Swayam Prabha. Digital India. Educated India.
Friends, let us continue our discussion on chemical reaction engineering and in particular reviewing some of the material that you would have already seen in your undergraduate class. Last time we reviewed about stoichiometry of the reaction. So, for example, we saw how we can represent a chemical reaction, a single reaction or a multiple reaction, how we can monitor the progress of this reaction by way of presenting the extent of reaction or conversion of a reaction. And we also saw the idea that in a reaction there may be one component which will get exhausted first, or in other words it will become stoichiometrically limiting. So, let us now continue our discussion bringing in thermodynamics in the domain of reaction engineering. Now, let us go back to the example that we considered in the last class, namely steam cracking of ethane, and look at what are the conditions with which we operate this reactor is typically operated. So, we have a tubular reactor. On one end of it we feed in ethane and we get unreacted ethane, ethylene, hydrogen and so on outside the reactor. Now, two things we had noted last time, that in this reactor we feed ethane and steam, and also the inlet pressure is specified at 3 atmospheres, fairly low atmosphere process, and temperature of about 700 degrees centigrade. Now, the question arises, why these conditions, why steam in the reactor, or why for that matter pressure is only fairly low, temperature is high and so on. And this is where thermodynamics comes into the picture. Let us take an example and see how thermodynamics plays a role. So, let us take a so we will look at equilibrium conversions in a reaction. We will look at how working conditions of the reactor are dependent on this equilibrium conversion and therefore on the thermodynamics of the reaction, and we also will look at heat effects in chemical reaction. So, these are the broad topics that we are interested in when we talk about thermodynamics of chemical reaction. Let us take an example to illustrate why thermodynamics is important. Let us say that we have this reaction A going to B, or A1 going to A2 if you like to call, and it proceeds with certain rate as represented over here. And we can carry out this reaction in a batch reactor and monitor the concentrations of A, that of B, and also the conversion in the reactor. You will recall the conversion in the reactor will be for this particular case will be defined in terms of species A, because that is the only species as a reactant. So, that is our limiting species. So, whatever A we had in the beginning Ca naught minus whatever is present at any time t, that is Ca, divided by Ca naught will give us the conversion. So, let us closely look at the progress of this reaction. So, on the x axis we have time. So, we are doing a batch reaction. So, we are taking let us say samples at various times, and on y axis is conversion and concentration of species A. Let us start with species A first, and shown in the blue line is the concentration of A as it changes as the reaction proceeds. And you can see that we in this particular example we have started with 2 mole per dm cube of A, and as the time progresses, this concentration slowly drops down as per the rate given by this expression, and after sufficiently long time in this case is about 4 hours, the concentration of A goes to practically 0, that means A is completely utilized. Concentration of B on the other hand increases from initial value of 0 to a maximum value of 2. Recall that the stoichiometric relation between these two is 1:1, 1 mole of A gives 1 mole of B, and therefore, when 2 moles of A are consumed, 2 moles of B are generated. We also have conversion, which we calculated as I explained just now, and this conversion again increases from a 0 value to value 1 or 100% if you are talking in terms of percentage conversion. So, this is how typically a reaction of the type A going to B is expected to behave, and indeed it does behave in that manner. But now let us try to look at how a reaction which can proceed from left to right as well as from right to left, or in other words we are now looking at a reversible reaction. So, it can go either way depending upon the conditions in the reactor, and we would like to know what those conditions are. We will come to that little later. So, this rate of this reaction now consists of two parts, one which represents A going to B. So, this is my term that is same as before, but in addition now we have B going to A, which proceeds at this particular rate, and therefore, our rate of reaction is the rate at which A goes to B minus rate at which B goes to A. And let us look at how this reaction proceeds. The terminology and everything else is same. So, we have A of 2 moles per dm cube or 2 moles per liter at the beginning of the reaction, and as time progresses it decreases, qualitatively similar to what happened in this reaction. However, after A has decreased to about let us say 0.6 mole per liter, there is no further decrease in the concentration of A, and in fact, however you may run this reaction beyond let us say this 3-hour time period, we always have about same value of concentration of A. That means, A is no longer consumed. Same thing is reflected in value of B also, and that of conversion. Conversion is increasing from 0, but it is not saturating at value of 1 as was the case over here. It is saturating at some intermediate value roughly about 0.6, 0.7, 0.72 or something of that order of magnitude. No matter what we do, that means continue the reaction for longer times, nothing is going to change. The concentrations are going to be at these respective levels, conversion is going to be same. Or in other words, now we have saturation not at the complete consumption of the reactant, but saturation at some partial consumption of the reaction. And why has this occurred? This has occurred because this reaction is reversible. So, we have A going to B, B going to A, and therefore, we have possibility that at these times has the reaction completely stopped? In a sense, yes and no. Yes, because we see that there is no more consumption of A. It has reached a saturation value, but also no in sense that what is really happening at this time at 4 hours, 5 hours and so on, that rate at which A is going to B is counterbalanced by rate at which B is going to A. So, there is a reaction taking place, A is getting converted to B and B is getting converted to A, but the rate at which they are getting converted are at the same value, and hence there is no net change in the concentrations, or in other words this reaction has reached equilibrium. Thermodynamics tells us lot about equilibrium, and hence we need to know at what conditions such saturation will occur. Now, operationally this is important, because for example, if you are designed your reactor to run for 3 hours, you are getting certain conversion. Now, it is natural to expect that if you run this reaction for a longer time, you will get little better, but that is not what is happening over here. Whether it is 3 hours or 4 hours or 5 hours, practically the conversion is same. So, any investment that you do in running this reactor for a longer period, such as 4 hours or 5 hours in this particular case, is not going to give you any additional returns. That means it is not a wise thing to do. Let us continue this same example and say that what we did discuss just now is what was happening at temperature if you maintain the temperature in your reactor of about 320 degrees Kelvin. I should point out that these numbers are not that critical, this could have been any, but whatever example I have taken, these are the numbers that are used. The behavior will be same even if those rates are different and so on. So, once again we see that there is a saturation in the rate. But what if I do this reaction at 330 degrees centigrade, that is same conditions, but reaction is now carried out at 330 degrees centigrade. And let us compare these two now, starting with A. Here the saturation is occurring at around 4 to 5 hours, and the value of concentration of A remaining in the reactor is about 0.6. But look at what is happening when we do the same reaction at 330 degrees, only 10 degree temperature difference. We notice that once again the saturation in concentration of A is occurring, but it is now concentrating, the saturation levels are about 1 mole per liter, not 0.6 as was the case here, and similar change is reflected in concentration of B also, which is going from a 0 value to a high value. Or in other words, qualitatively behavior is same, it is taking some time, but after some time there is no more change in the concentrations. So, behavior qualitatively is same, but quantitatively, that is number wise, the behavior is now different. Whereas, we got conversion of about 0.7 when temperature was 320 degrees centigrade, we get now conversion of only about 0.5 when temperature is 330 degrees centigrade. So, in other words, this conversion is dependent on what temperatures we use. This conversion is therefore can be said to be dependent on the operating conditions in the reactor, and these could be temperatures, pressures, what concentrations you start your reaction with, and so on. So, we would like to know all these factors when we try to design the reactor, because clearly any decision for this particular example to run a reaction at higher temperature 330 degrees centigrade is not a wise decision, because you are getting lower conversions. It is a good decision if you look at how fast we are achieving those conversions. We are achieving it much faster in only about half an hour compared to about 3 hours over here. And this example therefore illustrates another interesting aspect in design of reactors, that is how temperature influences your reaction. On one hand, if you carry it out at higher temperature, your reactions are apparently progressing very fast, very rapidly. However, they are progressing only to a limited extent, which is not favorable because you are getting lower conversions. So, there is a balance to be struck. Do you want high reaction rates or do you want higher conversions? We will come to this aspect of design during the course of my subsequent lectures. But at this point I want you to keep in mind that there is always a trade off when you try to design a reactor, particularly this kind of reaction. What is that kind of reaction? Let us now formally look at some of the developments that formulations that we use in a chemical reactions in the form of equilibrium. So, we start out with our general reaction, and at this point I will consider only a single reaction, that is taking place summation nu j A j equal to 0, taking place at constant temperature T, pressure P. Now, thermodynamics tells us that for any process to occur spontaneously, there is always an increase in entropy, such that the entropy keeps increasing, reaches a equilibrium value or the maximum value when entropy can no longer increase further. This is a broad understanding we all have from our thermodynamics 101 courses. Now, when it comes to using this information in form of for the case of reaction engineering, working with entropy is not an advantageous thing. So, we go to free energy and use Gibbs equation, which tells us that the change in free energy represented here as dG is V dP minus S dt plus summation mu j dnj. V is the volume of the system, P is the pressure, S is the entropy, T is the temperature, N is the number of moles of species in the system, and there is a quantity mu of j, which is nothing but the chemical potential of the species. Formally, what is the definition of mu j? Mu j is nothing but partial of free energy with respect to the moles of the species concerned Nj. So, del G by del Nj at constant temperature, pressure and composition of all species except J remaining same. Or in other words, it is a amount by which the capacity of the phase to do work changes by incremental addition of small quantities of species Nj, everything else kept the same. So, we have this chemical potential which define which comes in this Gibbs equation. So, the question now is, how do we use this information? Let me step back and what information are we looking for? The example which we saw a few minutes back showed us that as reaction proceeds, first there is a change in number of moles of various species, but after some time saturation is reached. So, we want to know what is that level of saturation, or in other words, to what extent my reaction will proceed. I want to know what will be the conversion when my equilibrium is attained. So, we are using thermodynamic information to gather that information, and with that we have started with Gibbs free energy. So, let us come back to this Gibbs equation. Same equation, dG equal to V dP minus S dt plus summation mu j dnj, j going from 1 to n, that is all species put together. Now, from our yesterday's or last discussion of stoichiometry of the reaction, we know we have a measure to monitor the progress of reaction, namely the extent of reaction. and according to that definition of extent of reaction, the number of moles Nj at any point of time is number of moles Nj0 that we started with plus nu j into extent of reaction alpha. This we had seen in our last session. This now implies that incremental change in number of moles is directly proportional to incremental change in the extent of reaction. I am just taking a derivative of both sides. Nj0 is constant because that is a fixed value, nu j is constant stoichiometry. So, dNj is nu j d alpha. So, now if we now substitute dNj equal to nu j d alpha into our Gibbs equation, now we get free energy change dg is equal to V dP minus S dt equal to summation j equal to 1 to n nu j mu j d alpha. Now, what happens when reaction proceeds? So, let us say that we have some measure of how the free energy changes as the reaction proceeds. Recall that we said entropy increases, the free energy of the system decreases. So, let us say on y axis we have some measure of free energy, and on x axis I have my extent of reaction. So, this is my starting point, that is some free energy. So, as reaction proceeds, my free energy changes, reaches a minimum value, and this is the point at which my reaction will stop, because that is a minimum value. So, on the other side I expect that free energy will increase. So, for my reaction A going to B, my free energy is going to decrease, reach a minimum, and if you are looking at from this side, it is minimum at this point. If you are looking from B going to A, then same thing will happen, the reaction will reach a minimum. So, this is the point at which my reaction will come to an halt or come to an equilibrium state, and this extent of reaction at which my G free energy is minimum, I call it as alpha E, that is extent of reaction at equilibrium condition. So, what is that equilibrium condition? We have this Gibbs equation which we have represented it in this particular form. So, we have dg equal to nu j mu j d alpha. So, if we are looking for that value of alpha at which free energy change is minimum, then mathematically this condition can be expressed as del g del alpha at constant temperature and pressure. So, we take derivative of this with respect to alpha, partial derivative, by maintaining pressure and temperature constant, and we get that condition now as that summation nu j mu j, this quantity over here, summed over all species j equal to 1 to n must be 0, and this is my condition of equilibrium. That is product of stoichiometric coefficient into chemical potential of a species and combining contributions from all the species summation, that must be equal to 0, and this is my condition of equilibrium. So, we now know what from our Gibbs equation, what is my free energy, what is my condition of equilibrium. we are only a step closer to getting what is this value of alpha at equilibrium. We are on our way. So, what do we now need? We need how is this condition related to the extent of reaction alpha. If you look at this condition as it stands now, nu j is the stoichiometric coefficient. So, that is given for a reaction, there is nothing changing there. So, it implies that if this condition is to give me this value of alpha E, then that alpha must be somehow influencing this chemical potential mu of the species. In other words, to take this discussion forward, we now need another set of equations which relate chemical potential of the system to the progress of reaction. So, let us proceed in that direction now, and I will be discussing only few illustrative possibilities. There are many more possibilities of this kind, and excellent discussion on this appears in a book by Denbigh called Chemical Equilibrium. This book is fairly old, but the material is classic. The author is Denbigh. His book name is Chemical Equilibrium. Okay. So, let us look at how we move forward. So, let us say that we are carrying out a reaction and all components of this reaction are in the gaseous phase, and this gaseous phase behaves as a perfect gas mixture. Then the chemical potential of the component J at given temperature, pressure and composition. So, T is temperature, P is pressure and Y is the composition. So, we have n components. So, in terms of mole fractions Y1, Y2, Y3 mole fractions is equal to or is related to some reference condition chemical potential mu j 0 at given temperature or temperature of interest, reference pressure and reference composition, plus R T ln P y j. P is the total pressure, y j is the mole fraction of component J. So, P y j is nothing but the partial pressure of component y j divided by reference pressure. What is reference pressure? Reference pressure is typically taken as 1 atmosphere and reference composition is taken as pure J. So, reference composition Y R will have components all zeros except jth component unity, that means mole fraction of J is 1, that means we are looking at pure J. So, this is how chemical potential is related to temperature and pressure and the composition. That is a model that we use. But what if gas is not behaving as a perfect gas mixture? Then we have non-ideal gas mixture behavior, where we define the chemical potential for given temperature, pressure and composition, once again relating it to its reference pressure plus R T ln fugacity of J by reference fugacity. Reference fugacity is again taken as 1 atmosphere or pressure, reference pressure of 1 atmosphere, and we have fugacity. What if reaction is taking place in a solution, liquid solution, let us say? We have a similar definition. Chemical potential as a function of temperature, pressure and composition x as related to the standard condition chemical potential plus R T ln gamma j x j. R T ln gamma j x j, gamma j is the activity coefficient, Xj is the composition. Or in other words, we have different models depending upon how we view our solution, the reacting mixture is, whether it is a perfect gas mixture or it is a non-ideal gas mixture or if it is a liquid solution and so on. So, in a compact or more simpler form, we can write mu j equal to some reference condition chemical potential mu j plus RT ln activity of J, okay. And this activity of J, for example, when the gas is perfect mixture is partial pressure of J, it is fugacity of J when it is a non-ideal mixture, it is gamma I xi gamma j xj when we are looking at solution and so on. So, this is just a simplified representation of our chemical potential, mu j equal to mu j 0 RT ln Aj. Okay. So, we have the equilibrium condition summation mu j equal to 0. We have appropriate model of how chemical potential depends upon the properties of the reacting mixture, namely temperature, pressure and its composition. So, now next step would be putting these two pieces of information together. Remember, our ultimate goal is to find what is the maximum or equilibrium extent of reaction alpha E. So, we have equilibrium condition, we have a model for a chemical potential, yet it is not apparent that alpha E is appearing anywhere in the picture, or for that matter alpha is appearing anywhere in the picture. So, let us try to bring that in now and complete this discussion to get alpha E. So, let us take a specific example now. Let us say that we have 4 components A1, A2, A3 and A4, and let us say that we have stoichiometric coefficients nu1, nu2, nu3, nu4 and this is my reaction. I know my chemical potential as related to these operating conditions, temperature, pressure is given in this particular form. Let me now multiply this chemical potential by nu j and add it up for all the species. So, what do we have here? Nu j mu j summed over all n species is mu j 0 nu j summed over all species, that is all reference chemical potentials put together, plus RT, the real terms will be nu 1 ln A1 plus nu 2 ln A2 plus nu 3 and so on. So, nu j ln Aj, and we know summation of ln's with nu j ln Aj is nothing but ln of product of Aj raised to nu j, or all we are trying to do here is we have nu 1 ln A1 plus nu 2 ln A2 and so on. So, this I can write it as A1 raised to nu 1 plus ln A2 raised to nu 2 and so on, or this ln A1 raised to nu 1 ln plus ln A2 raised to nu 2 is nothing but ln of A1 nu 1 into A2 nu 2 and so on, and that is nothing but this product term. So, now I have my equation for free energy change by summing it up for all species in terms of reference conditions and in terms of all the activity of all the species, or in other words, now we represent it in a slightly different form, that this is my free energy change delta G, as it relates to the standard condition free energy change, which is summation nu j mu j 0 standard condition free energy change plus RT ln product of A j raised to nu j and product carried over all the terms of this equation. So, this free energy change, what should happen to this free energy change at equilibrium? Let us move little further. So, we have our free energy change as free energy change delta G 0 RT ln A j nu j A j nu j A j raised to nu j summed over all this. So, this free energy change at equilibrium must be 0. So, free energy change delta G at equilibrium is 0. So, this is my condition, and I express this product of A j raised to nu j as an constant equilibrium constant K A. So, write this condition as delta G 0 RT ln K A, which is must be equal to 0, or K A is nothing but this product, which is exponential minus delta G 0 by RT from this equilibrium condition. So, my equilibrium constant K and this subscript A is denoted to say that I am expressing all my activities as AJs. So, my composition is expressed in terms of AJ. So, I am referring to this equilibrium constant with a subscript A. So, this is my equilibrium constant related to the standard condition free energy change delta G 0 divided by RT, and standard condition free energy change is nothing but summation of product of nu and chemical potential at standard condition. We can actually choose to express our compositions in various different forms depending upon how we view our mixture. So, this constant, if for example, if I use partial pressure for activity, that is pure gas perfect gas mixture, then I use term Kp subscript P denoting we are now referring to equilibrium constant in terms of pressure as product of partial pressure of J raised to nu j, or fugacity Fj raised to nu j product of all those terms as Kf. Or if we choose to express composition of the reacting mixture in terms of its concentrations, then we have equilibrium constant Kc, which is this product. So, depending upon how we choose to represent our composition, we will have different definitions and different equilibrium constant. But important to remember this thermodynamic property, that is that equilibrium constant is minus delta G 0 by RT, and one can actually show a definite relationship between all these different kinds of relationships. Okay. So, now let us try to now see how we bring in our equilibrium composition from our free energy change. So, let me reiterate that our equilibrium constant, and let us say we are measuring in terms of pressures, is exponential minus delta G 0 by RT. Okay. This is a thermodynamic property. This is a thermodynamic property because all these quantities delta G 0 in particular, thermodynamics gives us that information. So, again what is this delta G 0? is nothing but summation nu j mu j 0. So, this is my thermodynamic property and its function of temperature alone, because our mu j zeros are function of temperature. So, this is my thermodynamic quantity. My next job now is to, having known this equilibrium constant from thermodynamics, how do I calculate my equilibrium extent of reaction, and that is what we will quickly do it, going step by step. So, let us say that my equilibrium constant is Kp, defined in terms of partial pressure of j raised to nu j over product. But what is partial pressure after all? Partial pressure is nothing but the mole fraction into total pressure. And what is mole fraction? Mole fraction is nothing but number of moles of Nj divided by the total moles in the reacting mixture. So, Yj is nothing but Nj by Nt. So, Pj is nothing but Nj by Nt into pressure. Now, we are a step closer, almost there. What is our Nj? As per our definition of extent of reaction, it is Nj 0 plus nu j into alpha. So, now if I put if I put this Nj over here, I have my top term over here. For instead of Nj, I have put Nj 0 plus nu j into alpha. And what is Nt? Number of moles, total number of moles is nothing but summation Nj. So, summation Nj is nothing but summation Nj 0. So, which I have called Nt 0, total number of moles initially present, plus summation nu j into alpha. So, I can write it as alpha summation nu j. So, my equilibrium constant now is the total pressure P into this function over here, which is nothing but representing the mole fraction Nj by Nt raised to nu j, because that is my definition of equilibrium constant. So, now we see my equilibrium constant Kp is equal to this value, and here we have alpha now appearing for the first time, or in other words, now my equilibrium information, that is Kp is minus delta G 0 by RT. So, knowing the value of Kp from thermodynamics, I can now solve this equation. I am representing this whole function as some function f of alpha for sake of simplicity. So, knowing this value, we can solve this function for alpha and get that value of alpha e, or in other words, what will be our alpha e? Our alpha e will be Kp equal to f of alpha e. That is, Kp is known independently from my thermodynamics, or let me write it over here. Kp is equal to f of alpha e. I know Kp independently from my thermodynamic information. I have this function, I know what is the function, this function f. So, that value of alpha which satisfies this equation is my equilibrium extent of reaction. Okay. Let's work out a simple example to make this idea clear. So, let's consider our example of our carbon monoxide formation. So, I am going to repeat this whole example. Carbon monoxide plus 2 moles of hydrogen gives rise to 1 mole of methanol. Let me call this species as A1, this as A2, that is carbon monoxide is A1, hydrogen is A2 and methanol is A3. So, we can quickly write this reaction as A3 minus A1 minus 2A2 equal to 0. So, my stoichiometric coefficient nu 1 is minus 1, nu 2 is minus 2 and nu 3 is plus 1. What is my condition of equilibrium? My condition of equilibrium is nu 1 mu 1 plus nu 2 mu 2 plus nu 3 mu 3 equal to 0, that is summation nu j mu j, which is this. So, this is my condition of equilibrium. So, which means if I substitute values of mu 1, mu 2 and mu 3 minus mu 1 minus 2 mu 2 equal to 0. Okay. Let's come to mu 1. What is my mu 1? I am going to use perfect gas mixture behavior. So, mu 1 as a function of temperature, pressure and all the other quantities. So, let me remove it. Mu 1 is mu 1 0, which is a function of temperature, plus RT ln partial pressure of 1, that is my mu 1. So, that is my perfect gas mixture model. Similar quantities for mu 2 and mu 3. So, now if I substitute these individual values over here, I will get summation nu j I j. So, let me clear some. So, I am just substituting the values of mu 1, mu 2, mu 3 in this equation, and what I will get is mu 3 0 minus mu 1 0 minus 2 mu 2 0, okay, from this first terms over here, plus RT ln P1 raised to nu 1. So, P1 raised to minus 1 into P2 raised to minus 2 into P3 raised to 1, that is product of Pj raised to nu j ln of that. So, this is that product. So, now let me continue this discussion further. So, my free energy change which I had earlier defined as summation nu j mu j will be free energy change at standard conditions, and these values you know from these values you know from thermodynamics, plus RT ln P3 divided by P1 square P1 raised to 1 P2 square. What is my partial pressure P1? Total pressure into Y1, total pressure into N1 by Nt, and similarly all other species, and this is now will give me my what is N1? N1 is N1 0 plus nu 1 into alpha, and Nt is Nt 0 plus alpha summation nu j. So, this is what gives me how I get my equilibrium composition. So, now if I put it over here, my Kp equilibrium is P3 by P1 P2 square, and each of these P3 P1 P2 will have this term alpha, and that is how Kp is related to alpha. We will stop here and continue this discussion on how thermodynamics gives us more information in our next session. But before we do that, let us try to recap what we saw today. We first of all demonstrated or saw for first hand Why thermodynamics is important? It is important because it tells us about the equilibrium conditions, it tells us about what operating conditions one should follow. To get that information, we started with Gibbs equation, essentially the idea being that if entropy of the system occurring progressing spontaneously is increasing, the free energy decreases. So, we made use of Gibbs equation, got the condition of equilibrium, which is summation nu j equal to 0, and then brought in by using appropriate model for chemical potential the composition, temperature, pressure dependency of chemical potential, that is if it is a perfect gas mixture we have in terms of partial pressures and so on, and then use this condition to get my equilibrium constant Kp and relate it to my extent of reaction. How we use this information will be the subject of discussion in my next session. Thank you.